Hello, Honors Chemistry, and welcome to the Chapter 6 review. So first of all, don't forget that Chapter 5 is essential to Chapter 6, and so is Chapter 1, 2, 3, and 4. But Chapter 5 has review videos posted already on PowerSchool, so make sure you use those as part of your review process. In addition, there are all the blank practice copies for naming that are on PowerSchool, all of which are great resources, so make sure that's part of what you're reviewing as you prepare for this test. All right, so getting started with the Chapter 6 review. So looking at number 9, we are tasked with finding the proper name for a compound composed of that, and that percent of C, R, C, and O. So first we are going to take our percents and we are going to convert them to grams by assuming we have a 100 gram sample. Then we'll take our grams of each and we'll use molar mass as a conversion factor to get from grams to moles, okay? We are never going to compare one element to another in grams because grams is not a counting unit, right? Grams tells us an amount, but it doesn't let us count how many particles there are, right? Because a particle of chromium has a different mass than a particle of carbon versus particles of oxygen, right? So we have to convert them to moles first. So grams to moles using molar mass. All right, next step, we are going to write our formula using the values we got, right? So chromium 0.7042, carbon 1.055, oxygen 3.17, now, or 3.169. Do be mindful here, it's important we don't round, okay? We don't round till the very end. You would just perpetuate the number in your calculator. If you're using one of your middle school calculators, you could round to 3 or 4 decimal places, but nothing less than that. Otherwise, you're not going to get the right numbers. So anyway, we are going to, because we have to have whole number ratios, because atoms don't exist in decimal form, right? You can't have 0.7 of an atom, right? So we're going to reduce by the smallest piece, which is 0.704, which means divide everybody by that value. And we're going to get 1 chromium to 1.5 carbons to 4.5 oxygens. That's the ratio we're going to get. Now, we need to think to ourselves, ooh, we can't have 1.5 carbons. That doesn't work that way. But 0.5, if we multiply by 2, because 0.5 is 1/2 as a fraction, is going to get us to whole numbers, which means you have to multiply all of them by 2, and then we get the correct empirical formula, and we'll jot that down. Now we have to actually answer the question. So we'll look at our compound and realize, well, we have a metal and we have these other things, so it must be an ionic compound that contains a metal and a polyatomic ion that we recognize, which would be CO3. That's the only one composed of carbon and oxygen, right? So we would rearrange it to say that. Then we would just solve for the charge of chromium because it's a type 2. So we know that carbonate has a charge of -2, and there are 3 of them. There are also 2 chromiums, which means that X must be 3. So chromium 3 carbonate. Right. Next up, we have a similar but not the same problem where we're given a mass of titanium oxide. Okay, it doesn't give us a charge, meaning we're trying to figure that out. And it has 7.33 grams of solid metal, so titanium, and some gaseous oxygen. Here's where we're going to use our law of conservation of mass. If we have 28.92 grams of a compound that contains some titanium, some oxygen, and I know that there must be a total of 17.33 grams of titanium, the difference gives me the mass of oxygen also present in the compound, again, courtesy of law of conservation of mass. Yes? Fantastic. On to the rest of the problem. All right, so now we know the mass of titanium and the mass of oxygen. So similar again, but not the same. In the previous problem, we had percents, which we then assumed were grams, and we proceeded, right? Now we're given grams, so we don't have to assume anything. We're just going to start from our grams and convert them to moles, again, using molar mass as our conversion factor, right? If you'll think back to the quiz and to your EOCs, sometimes we're given moles, which means that we're one step closer even still, right? And it's a little bit less work to do, right? So we always need to stop and assess, which is why it's important that we've memorized the steps for solving for an empirical formula, so that way we will recognize where we're starting from, okay? So anyway, we'll start from our grams, use molar mass to get to moles of each element, and then we will write our first pass at the formula using the numbers we've got, bearing in mind that we can't have decimal pieces of atoms, so we are going to reduce by dividing by the smallest piece, which in this case is 0.362, which is going to give us 1 titanium and 2 oxygen. Now, the question asks us for the formula, no, for the proper name, so that means the formula is just step 1. The last problem, now we've got to work to figure out the charge of that titanium because it's a type 2 metal. So the charge of oxygen is -2 and there are 2 of them. There is only 1 titanium, which means X, or the charge of titanium, must be 4. So then our proper name would be titanium 4 oxide. Okay, now moving on to some problems where we're going to employ some Avogadro's number. So, how many molecules are in 15 grams of phosphorus hexafluoride? So clearly we need a formula. It is molecular, so we're just going to follow our prefix here, which says PF6. Now, we're going to start from our grams. In order to get to molecules, first we got to get to moles. And in order to get to moles, we are going to need... That's right. We're going to need to calculate the molar mass of phosphorus hexafluoride by adding together all of our pieces, right? So 1 phosphorus and 6 fluorine. And when we get that added all together, that's going to give us the molar mass, bearing in mind that the units of molar mass are grams equal to 1 mole. So we do make sure we put all our pieces in the right spot. Now we are at moles, and the next step is to get from moles to molecules. Here is where it's important to remember that we have to use the right word for the right particle, right? Here, PF6 is a molecular compound, so molecules is the appropriate word, and so this makes sense, and we've probably set it up correctly, and then it's just a matter of making sure we do the math right at that point, okay? So do be mindful. Then we're going to move on to number 16 and talk about how these two questions are different. So first, if we look at 16, it says how many atoms of fluorine are in 15 grams of phosphorus hexafluoride. So let's say 15 was not the question right before this, right? We would know that in this case, right, we're starting with grams of a compound that we need to break into its respective pieces, right, in terms of doing our math, right? So that's going to tell us, well, first, we need to figure out how we want to do this relationship, right? The way we did number 15 is a good way to start, where we could start from our grams of our compound and just figure out how many particles of compound there are, bearing in mind that we can't just say atoms of, PF6, because that doesn't make sense. PF6 is a molecule, so we would use the term molecule, right? So really, all that work for 15 are the first 2 steps we would do for number 16 anyway. So what I decided to do was start from our molecules and figure out how to break down my molecule. I know that 1 molecule of PF6 is equal to 6 atoms of fluorine, right? That is a particle relationship based on the formula. So once I've figured out the molecules of PF6 present in 15 grams, which is the work we did in number 15, right? Then I can take my molecules of PF6 and incorporate that last conversion factor, which is going to take us from molecules to atoms. Alternatively, there are mass relationships we could do. There are mole relationships we can do. There are lots of routes to get to the final answer. So you're more than welcome to bring your work or show me your work, and we can talk about if your method is correct or not. All right, so now flipping to the next page, we're going to work a relatively simple problem, but one where if you don't understand what percents mean, it can feel very difficult. So it says that a hydrocarbon is composed of 92.24% carbon. When we say that something is, any percent something, we need to know what that means. Sorry for the weird iPad moving. But anyway, when we say that, and remember ours are by mass, it means that we have 92.24 grams of carbon equal to every 100 grams of compound, which means that every time you see a percent, that's more often than not going to be a conversion factor, right, between the piece, in this case carbon, and the whole, in this case the compound, right? So the question says I'm starting from 5.22 grams of the compound, and I want to get to carbon, so I just need to make sure I use my conversion factor correctly. Some of you guys mixed that up on the quiz because you didn't pay attention to units, right? So make sure that you're always writing your units. That is key and clearly something I will be looking for and grading. Okay, and now we flip to the last page, and here are the answers to the very last problem, which kind of go hand in hand with the math that you guys are doing for the nutrition activity anyway, right? In terms of being able to read the information off of a nutrition label and apply all the math and chemistry things that you know, right? So solving for A, when it says what percent by mass of a serving is sugar, you would look at that nutrition label and figure out, oh, well, there are 10 grams of sugar per serving. One serving is 28 grams, so there are 10 grams of sugar per 28 grams of popcorn, which we can then figure out the percent sugar per serving, right? In B, if we want to find the percent by mass of serving that is sodium, we do the same thing. We would take our milligrams of sodium and convert them into grams, and then we would take our 0.220 grams of sodium and divide it by 28 grams serving, and that gives us our percent that is sodium, right? C says to look at the ingredients and figure out the likely sources of sodium. Well, the likely sources of sodium are the things we know contain sodium, right? Salt in common use refers to sodium chloride. Baking soda, life things you should know. The proper name for baking soda is sodium bicarbonate, and the sodium phosphate, right? Those are all places or sources of sodium based on the nutrition label. And if we look at D asks us to take 1 pound of popcorn and figure out how many grams of protein, right? So we would start with our 1 pound, and then we would figure out the relationship between pounds and grams. That's back in chapter 2, right? And then we would figure out, well, we already know that 28 grams is 1 serving, and that 1 serving, based on the nutrition label, contains 2 grams of protein, right? And ta-da, we've done our conversion, right? Looking at E, we would do the same thing. Here we're starting from half a cup of popcorn. So half a cup of popcorn, and then we would know that 1 1/4 cups of popcorn are equal to 28 grams of popcorn. That's what the nutrition label also says. 28 grams of popcorn are equal to 10 grams of sugar, right? And then we'd use the molar mass of sugar and then Avogadro's number to get to molecules of sugar per serving, right? So here is where all of that chemistry stuff ties in and things we can do, and we can calculate how many molecules of sugar we would eat, right? Look at the cool things you guys can do. All right, study. Thank you for listening. Be good, and I will see you soon. All right, bye.